this is going, and then I will share my screen in a second, guys, as you guys are here. Zachary says, glad to be here, excited for the second semester. You saved my life last semester. That's a very big statement, and I thank you. Happy to hear that. Yeah, I'm glad, guys. Like, this is community has been a wonderful addition and something that I've wanted to do for so long, and I'm so thankful it's finally coming to, to life as to what I wanted to create. And great. Let's see. Okay. So before jumping in, as you can tell, Cooper's here and he has an awesome lesson for you today and review today. I'm going to go ahead and just share the video that I recommend. And it is this one. So right now, what we're going to go over is like a quick review of the reactions. However, if you want a longer review, which I do recommend watching, it's going to be this video, which I'll put in the chat as well. But this is the one that covers all of the different reactions. So you'll see that here with SN1, SN2, all of those identifying. Same with the reactions that you'll see later on, like it actually gives you the tables. Plus, for our community members, of course, you guys will find the PDF. So that is extremely helpful to keep. So that's the PDF with the reactions, like these sort of tables that I have, that's already there for you. So you can quickly look at them whenever you may feel like you forget it later on. I recommend checking that out. And then, which again, I'll put that in a second in the chat. But I also wanted to explain how this tutoring, this weekly live tutoring is working right now. So right now we do have this open for community members to be able to see what this looks like and get a feel for what tutoring is with Cooper. And what the benefit of this is the fact that you actually get to decide what these sessions are going to be as the semester begins. So you'll be able to ask your question, post that on the actual community page that we have here for you. It says OChem Live Tutoring. How it works is the team will post pretty much an area of where you're going to comment your questions for the next week's live. And that's what Cooper is going to be picking from and taking those questions to answer them on the live. So you guys really get to decide what that live is going to look like, which is the beauty of this. It really is tutoring. So that's a huge benefit. And it will eventually just be for premium members. So I highly recommend making sure you lock in your spot for premium members because maybe if we're capped and we see we have too many premium members, we might close it off. So I want to make sure that you guys secure your spot so you can ask your questions. And also, of course, we do have a huge library that you guys are going to see there. So depending on when you start your class, you can always go over the reviews that we have, part 1 and part 2, or of course you can then start off with, maybe you start off with alcohols or you start off with aromatic compounds. That's another great way to be able to get ahead. So that's pretty much the main thing I wanted to share with you guys. Again, I'll place that link right now with the review. This is the OChem review that I recommend watching. And kind of a disclaimer here is, again, right now what we're going to focus on is pretty much diving into synthesis questions. That's what Cooper's is going to focus on. And he will go over some of the reactions. But again, we can't necessarily cover an entire OChem 1 reactions in like an hour, So, and we want this to be more practical for you, so to actually try synthesis questions. Also, I will be in the chat while Cooper is doing his thing and going over these questions. And of course, you guys can also download, by the way, you can download the PDF and all the questions that are there on the actual live page that you are on for the live stream. So I'll go ahead and let Cooper take it away. If at any point you guys have questions, please feel free to put that in the chat and go for it, Cooper.
Sweet. Alrighty. Thank you, Melissa. And like she mentioned, we do have a lot to cover today, so we're just going to dive right into it by doing a lot of practice problems with those common reactions that'll carry over from OChem 1 into Organic Chemistry 2. And then at the very end, we will go through some synthesis problems just because I know it has been a bit of a break for some of you, and I just want to make sure that we are yet again comfortable approaching those questions. And in terms of community members, please ask any questions about the material that you do have in the chat, just because this is a lot of information that we will be covering. So don't be shy. Feel free to put those questions in the chat. But from there, we're going to dive right into it. And like Melissa mentioned, we're not going to cover every single one of these reactions, but instead, what I'm going to do is just cover some of the common trends we will see with some of the functional groups in terms of like alkenes, alkynes, and some things we do need to watch out for. But for the really important reactions that we will cover, especially during those practice problems, I will take some time to go a little more in depth. Now, the first reaction we'll go through and just kind of review is just free radical halogenation. And the main goal of this reaction is we're turning an alkane into an alkyl halide. Now, the reason we would want to use this, say in terms of synthesis, correct, is an alkane doesn't really have any functionality. There's no polarization, it doesn't really want to do anything. But if we undergo free radical halogenation, we can now add a halide, more specifically an alkyl. We can add bromide or we can add a chloride. A lot of the times we will see that we'll be forming alkyl bromides, but by doing this, we're adding functionality to our molecule. If we look at this carbon, there's no partial charges, but now that we added a bromide to that carbon, we now have a good partial positive charge on this carbon, and then from there, we can undergo some reactions. So that'll be the main theme of today's lesson, if you will, is we want to find where those sites of reactivity are. Now, in terms of SN2, SN1, E2, and E1, I know you probably just sighed at those reactions as I read them aloud, but we'll go ahead, take a second just to review some of the very important things from these reactions that we do need to keep in mind. Now, the first thing we'll go over is SN2 reactions. Now, the important things about these reactions, or in terms of SN2, I should say, is SN2 relies a lot on steric hindrance. So if we are looking at the substrate, the best substrate we could use is something like an alkyl, we can use like a methyl bromide, for example. A methyl bromide, super small, super compact, and when our nucleophile attacks that carbon, since there's not any surrounding alkyl groups around it, we lack that steric hindrance and it's a lot more favorable to attack. And we can see we are lacking a tertiary substrate, and that is because a tertiary substrate, to refresh your memory, has too much steric hindrance, and it'll be a lot harder to undergo backside attack. And then in terms of E2, we'll be looking at a strong base. And what we're doing with E2 is instead of undergoing a substitution reaction where we're changing one functional group into another functional group, we're actually eliminating a functional group to form a functional group. More specifically, we'll eliminate a hydrogen and a leaving group to form an alkene. And that'll be done with a strong base. And in terms of SN2 and E2 reactions, what's nice about these reactions is they will not undergo any carbocation rearrangements. More specifically, because they don't form any carbocations, the main theme behind those is that they are concerted reactions. And if you forget what that means, a concerted reaction is a reaction that happens all in one step. Moving forward with SN1 reactions, we have to keep in mind these will be forming those carbocations. Our leaving group will leave, will form a carbocation. And same with E1, we'll also be forming a carbocation. The main difference is that with an SN1 reaction, a weak nucleophile will be attacking a carbocation, as opposed to a weak base for E1 reactions will be undergoing an elimination reaction with that base stealing a proton, forming that alkene. And then in terms of rearrangements, since we are forming those carbocations, they can occur, so we will have to be aware of them. In terms of being able to favor SN1 and SN2, one thing that we do have to take note of in terms of the reaction rates for some of them is that we can have polar protic solvents or we can have polar aprotic solvents. And just to refresh your memory on what these mean is that we just have a hydrogen that we could steal. So think of protic meaning like a proton you can give off if we're reviewing some of that acid-base chemistry. So right here we have an alcohol with a proton that could be given off. And more specifically, the reason these are favored has to do with those hydrogen bond. Oh yeah, the hydrogen bonding that can occur. Because hydrogen in this molecule will have a strong partial positive, oxygen will have a strong partial negative. So in terms of SN1 reactions, it'll help stabilize that carbocation intermediate. And then for SN2 reactions, we prefer having polar aprotic solvents. So if we're looking at acetone, for example, we don't have any good hydrogens that we could steal very easily. But if we're looking at this carbon, it has a partial positive charge. And if we're looking at this oxygen, it has a partial negative charge. So since we still have that polarization, it can help us stabilize some of the things we need to look out for in terms of SN2 reactions. Now, in terms of our SN2, SN1, E2, and E1 reactions, here's kind of a broad overview of some of the nucleophiles you will see and some of the bases. But just to do a very broad overview real quick, in terms of SN1 reactions, all we're doing is substituting a leaving group, a good leaving group, with a weak nucleophile. So right here we have a good leaving group, we have a weak nucleophile, and we substituted and we added an alcohol right there. And then in terms of E1 reactions, instead of substituting a leaving group, we're actually eliminating a leaving group and we'll then be forming an alkene. E2, very similar, is that we will eliminate a leaving group and add in an alkene. So we're going to eliminate more specifically a leaving group and a hydrogen at the same time. And more specifically, we'll be undergoing, we'll have to steal an anti-periplanar hydrogen. And what that means is that opposite faces. So just say if our leaving group is wedged, our proton that we would have to steal should be dashed. So they'll be facing opposite directions. And in terms of E2 reactions, we could either form a Zaitsev's alkene, where we can see right here, it is the most substituted alkene we could form, or we could form the Hoffman alkene, where if we're looking at it, it is the least substituted alkene that we could form. And then to finish it off with SN2 reactions, we're substituting a leaving group with now a strong nucleophile. So right here is our good leaving group, and then we have our strong hydroxide nucleophile. It will attack that carbon and substitute with that leaving group to form our product. Perfect. And then in terms of alkenes, one thing we need to note is that our alkene now can act as a nucleophile, or it can also act as a base. And in terms of reactions with alkenes, one of the most important things we need to be aware of is the difference between a Markovnikov addition versus an anti-Markovnikov addition. So what does that mean again? Markovnikov addition means we want our nucleophile to add to the most substituted position. So say if we're looking at this alkene, we can think of this carbon as a secondary carbon, if you will, and then this one as a primary carbon. And since this one is more substituted, meaning it has more groups coming off of it, our nucleophile will add to that carbon, which we can see right there. And then if we're looking down here, we have an anti-Markovnikov reaction, meaning our nucleophile actually added to the least substituted carbon. Now, in terms of regioselectivity, which we just covered with the Markovnikov and the anti-Markovnikov reactions, we can also have stereoselectivity. So we can have what are called anti-additions and syn additions. And what that's looking at is what is the relationship between the new groups that we just added across the alkene. So for example, if we're looking at a halohydrin that we just formed, this alcohol is wedged and it's an anti-addition because our halide that we added is dashed. So since one is wedged facing another direction and then one is dashed facing the other direction, it's going to be an anti-addition. And then if you look down here at our epoxide, great example of a syn addition since what we added is on the same side. And again, here's a good example of an anti-addition. We have one alcohol being wedged and then another alcohol being dashed. And then down here, great example of syn addition where both our alcohols are wedged and they're facing the same side. And then here's a good overview of some of our oxidative cleavage reactions where we can cut our double bonds in half, if you will, and we can form carboxylic acids depending on which type of alkene we have. But then if we go into ozonolysis, another great reaction in terms of cleaving that alkene and then forming carbonyls. So we can, for example, if we cut this bond in half, we can form an aldehyde, and then also, yeah, we can form an aldehyde right here. And then by cutting it in half, we show the other carbon that would have formed right there. So that's just a good example of how we can have our carbon chain, and we can actually break apart that carbon chain by slicing that alkene in half and then forming carbonyls from it. And then in terms of alkynes, only a couple of things to note with these reactions is we can still have Markovnikov and anti-Markovnikov additions. So whenever we have an alkyne, correct, that alkyne is between two carbons. And if we're looking at this alkyne, we have a carbon right here that is more substituted than the one on the end. So this is the difference between a terminal carbon versus that internal carbon if we're looking at an alkyne. And in terms of a Markovnikov addition, if we're looking at a hydration reaction, we can see that our carbonyl, our ketone, was added to that secondary carbon right here, that more substituted one. And then if we're looking at an anti-Markovnikov reaction, we can see that our carbonyl was added to that terminal carbon. So yet again, that's just showcasing, are we adding to a more substituted carbon or are we adding to a less substituted carbon? And whether it's, reactions with alkynes or alkenes, I will note that it's a lot easier if you want to review these reactions to make sure you really know your anti-Markovnikov reactions. Because if you know the anti-Markovnikov reactions, you automatically know the Markovnikov reactions. What I mean by that is that there's so few anti-Markovnikov reactions. If you know those few anti-Markovnikov reactions, the rest are just Markovnikov reactions by default, which we can think about it that way. And then one last thing I will note in terms of alkynes, something we need to be aware of is that we can use them to extend the carbon chain. So how can we do that? Let's look at this example right here. If we're looking at an alkylation reaction, if we remember reviewing our acid-base chemistry reactions last week, if we're looking at a terminal hydrogen that's coming off of an alkyne, that hydrogen is unusually acidic for an alkane, not an alkane, sorry, a hydrocarbon. And that's because we have some orbital effects that help stabilize that conjugate base. So what we can do is we can expose a super strong base in the presence of our alkyne that does have that terminal hydrogen that we can steal. And by undergoing that acid-base reaction, we can form a good carbon nucleophile, and that good carbon nucleophile can attack our alkyl halide if we were to include that. And by doing so, we form a new carbon-carbon bond, and we can extend the carbon chain, which is super beneficial. And in terms of that carbon chain, what we could also do is we could reduce that carbon chain. Just say if we don't want our alkyne anymore, if we want it to be an alkene, we can use these reactions and be specific with the actual stereochemistry behind it. Or if we wanted to go all the way down to an alkane, we could also do that in terms of our reduction reactions. But finally, we will get into the good stuff. So in terms of how these problems are actually set up, the first couple will be mechanisms, some important ones that we do need to know before you go into OChem 2. And then we'll be doing some predicting the product questions, which kind of have all of those reagents in order. And we just need to make sure we're comfortable with those reagents. And then we'll end off with synthesis. I know it's everyone's favorite, but I promise you, as we get more comfortable with it, it will be maybe a little more fun. You can think of it as a fun little puzzle. But to start off, for these questions, we'll be providing a reasonable mechanism for the following reactions. So whenever I'm given a reaction and I need to figure out the mechanism, the first thing I'm doing is I want to look. I know, Zachary, synthesis is scary, but we're going to get into it together. Sorry, for those who don't see the chat, our friend just commented synthesis with a scary face, which I feel like all of you are thinking that right now. But we will get into it and we'll be comfortable with it together. But yeah, to get back onto my train of thought, in terms of mechanism questions, the first thing I always do is I want to find where is my reactivity. Now, what I mean by that is I want to look at our starting material and I want to look at our reactive carbon. Which carbon can we actually react with? And if I'm looking at it, this carbon right here, since it's bonded to our bromine, yes, to our bromine, it has that partial positive charge, meaning we can undergo a reaction with it. And then if I look over at our product and I'm looking at which carbon underwent the reaction, we're looking at this tertiary carbon right here since it's bonded to this ethoxy group. So what this is telling me is that our reactive center, if that's how we want to think of it, is moving from this carbon, which I can show the corresponding one in the product. Our reaction, yeah, our reactivity is now moving to this carbon right here. So let's actually start by drawing the mechanism and maybe show a leaving group leave to see why that's happening. So we'll go ahead and draw out our cyclic structure, draw our wedged methyl, and then we now have our bromine. Now we have to remember bromine is a really good leaving group. And if we're looking at our solvent right now, we just have ethanol, which is a polar protic solvent. And if we were to go back up to those charts, that's telling me that since we have a polar protic solvent, and we also have a secondary leaving group, what can happen is an SN1 reaction. So we'll go ahead and write that down. So the first step of an SN1 reaction is our leaving group has to leave. So we'll kick out our bromine. And in this case, we will have equilibrium arrows, only because with a carbocation forming, that can go both in the forward direction and in the reverse direction. So we have our carbocation right here after that bromine left. So the next thing we have to do, and this is the biggest tip, whether you're taking OChem 1, OChem 2, whatever it may be, whenever you form a secondary carbocation, always look for a better one. So since we have a secondary carbocation, let's look over here. We still have a secondary position, but if we move up north a little bit to this carbon, we actually have a tertiary position. So since we have a tertiary position, we'll go ahead and include that dashed hydrogen. And what will happen is we'll undergo a hydride shift. So the electrons between this carbon hydrogen bond, the electrons right here will shift on over, which we'll go ahead and show that. And we'll undergo a hydride shift. So we'll draw out our single-headed arrows. I'm going to copy and paste that cyclic structure. And by doing that, we now formed a tertiary carbocation and we added a hydrogen to this secondary carbon. Now, one question you may be asking is why did I get rid of our wedged notation? Now, if we remember, whenever a carbon has a carbocation, what's happening is we're moving this carbon, which was sp3 hybridized, and it's now being changed to sp2 hybridized because p orbitals, or carbocations, I should say, reside in p orbitals if you want to think of it that way. So since we have a carbocation, we have a p orbital, and that means it's sp2 hybridized, meaning it's planar. So now that we have a carbocation, we also have to we have to keep in mind that we still have our solvent kind of floating around in solution. So since our solvent is still floating around, we'll go ahead and include that. And we can't forget that oxygen, it has those lone pairs. And since this is a weak nucleophile with those lone pairs, it will go through and attack that carbocation. From there, we'll go ahead and include those equilibrium arrows. So as that oxygen attacks that carbocation, we now form a new carbon-oxygen bond, just like that. And in terms of this, our oxygen is attacking that carbocation, but we're not getting rid of the hydrogen just quite yet. So we do have to keep that there. And since our oxygen, we'll include this, since our oxygen has 3 bonds as a good refresher and 1 lone pair, that means it will have a positive charge. So we'll include that. So from here, we're super close to our final product because if we're looking at this, we see that it is very similar to what we have, but we still have this hydrogen. So what we need to have happen is an acid-base reaction. And keep in mind, I know that on paper it looks like we have one molecule of ethanol, but when we're undergoing this reaction in lab, there's a whole bunch of ethanol molecules. So what will have happen is an ethanol molecule can actually act as a weak base, and it will steal that hydrogen. And as we steal this hydrogen, the electrons between oxygen and hydrogen, those will fall back onto oxygen to make a neutral, and we now have our final product. Perfect. So that's a good review of SN1 reactions, just a good review of just in terms of how to approach mechanisms in general. For this next one, what we'll do again is exactly what we did in that first problem. We want to find our reactive centers. So if we're looking at our starting material, we technically have two reactive centers, but it will be up to us to decide how those reactive centers will be reacting, if you will, which will be our partial positive, where we got to get that negative charge from. So if we're looking at this carbon, we see that it has a partial positive charge because it is bonded to our bromine. And then we are looking at this carbon as well. It also has a partial positive charge. So we have these two carbons we have to be aware of. But if we look at our product, we see that our bromine got kicked out as a leaving group and our oxygen is still there. And just by looking at it, we can see that our oxygen definitely attacked a carbon as it does have a new carbon-oxygen bond. So that's telling me that our oxygen actually acted as a nucleophile. But how did it act as a nucleophile? We can go ahead and draw everything out, get our long carbon chain. So if we're looking at this, we see that we have an OH group, but we can't forget about what is above our arrows. So we have sodium amide, we have NaNH2 right here, and we can't forget, I know it may be confusing or we do need to refresh our memory, but whenever we have a metal, that is just an annoying spectator ion that has a positive charge, which means our amide ion will be NH2, that nitrogen will have a negative charge. We'll go ahead and include that. Perfect. Now, since our nitrogen has a negative charge, we have to decide, okay, is it going to act as a nucleophile or is it going to act as a base? Because an amide ion can act as both. So if we're looking at our product, we can easily see that it won't be acting as a nucleophile, only because we don't see a nitrogen in there at all. But if we were to drag this over here, we have to keep in mind that acid-base reactions are very fast. So if we remember how I was talking about that our amide ion can act as both a nucleophile and a base, it does have the opportunity to attack this carbon right here, but it's not going to because it wants to undergo an acid-base reaction first because those happen a lot faster. So our lone pairs will steal our hydrogen, and then our electrons between the bond will fall back onto oxygen. Drag this over here. And we can now see that since our electrons have fallen back onto that oxygen, it has a good negative charge. And what we can see is that we have a good nucleophile and an electrophilic carbon on the same molecule. So what's going to happen is an intramolecular, we'll write down intra, and don't forget that intra means within the same molecule. This will be an intramolecular SN2 reaction. So we'll showcase the mechanism, and if we're looking at our product, we can see that we're going from a straight line structure, if you will, to a cyclic structure. So that's even more validation that our oxygen will attack that carbon on the same molecule. So we'll draw our curved arrows. Oxygen is attacking that carbon that's bonded to the bromine. And then these electrons will fall back onto bromine as we kick out that leaving group. And then we get our final product. Now, in terms of drawing cyclic structures, especially when we start out with a straight line structure like that, I always recommend to start counting at your nucleophile and finish counting at your electrophile. So let's showcase what that means. Like I said, start at the nucleophile and at the electrophile. Our oxygen is our nucleophile, so we'll give that a number 1. and then 2, 3, 4, 5. And the reason we're doing this is just to double check our work and make sure that we drew the correct cyclic structure. And after counting that, if I were to move up to our product, we'll start at the oxygen. We have 1, 2, 3, 4, 5. So since I counted the same, that means I drew it the same. And this is also a good way in terms of adding extra functional groups, which we'll actually see a little later on in this lesson. So just make sure, as we're getting comfortable again with synthesis questions, mechanism questions, whatever it may be, especially after a bit of a break, that we are still counting all of our carbons to make sure we don't lose any of those easy points, especially early on in the semester. We'll move on to our next question. So from here, what we're doing first is we are going to look at where our reactive centers are. Which carbons have functionality? If we're looking at our starting material, we see that we have an alkene right here, which means both of these carbons technically have functionality. They can react. So we have this alkene over here. And then in terms of our product, we see that we actually have the same number of carbons, but all that's happening is our alkene is moving from the end all the way closer to the middle. So as a good review, what's happening is we're starting off with a Hoffman alkene. And just to refresh your memory, a Hoffman alkene is when it is least substituted, and we're moving it to a Zaitsev's alkene, which is going to be more substituted. Perfect. And in terms of that substitution, if we're looking at this alkene right here, it currently only has one substituent coming off of it, which we can see is this bond right here. And then if we're looking at this alkene, there are technically 3 groups branching off of it. We have group 1, 2, and 3. Perfect. So to start off our mechanism, we will go ahead and include our Hoffman alkene. And in terms of the reagents we're given, we have concentrated sulfuric acid, which, to refresh your memory, concentrated just means you have a lot of it. So this is going to be more sulfuric acid, less water. And then we also have heat. So let's go ahead and draw out sulfuric acid. If I can draw out S, there we go. Perfect. And sulfuric acid, we can't forget, is a super, super strong acid. And whenever we have an alkene can also act as a base. So our pi electrons right here will actually act as a base. We'll steal that hydrogen, and then these electrons will fall back onto oxygen. And as we're doing that, we have to remember whenever we're undergoing reactions with alkenes, in terms of an addition reaction, as we're stealing this hydrogen, a hydrogen will be added to one of these carbons, and then a carbocation will go on the other carbon. And in terms of where our carbocation should go, we always want our carbocation to be on the more substituted carbon. So in this case, we have to pick between a secondary carbon and a primary carbon. A carbocation will be more stable on a secondary carbon. And speaking of secondary carbons, like we mentioned earlier in this review session, those are your worst enemies because you always have to be aware of if there's any rearrangements that can occur. So if we look over on the right side of that carbocation, we have a primary position. But if we look on the left side, we now have a tertiary position. So it's telling us that carbocation can be more stable on the tertiary position. Hydride shift will occur. Move that over towards that secondary carbocation. And then by doing that, we now have a way more stable tertiary carbocation, which is right here. Perfect. So from here, how can we form an alkene between these 2 carbons? Well, we can't forget that we have a conjugate base that is floating around in solution. And then also we have heat. So what this is telling me is that we can undergo an E1 reaction. So we have our hydrogen right there. And one thing about elimination reactions is that your hydrogen should always be beta to either the carbocation or your leaving group. Leaving group is more specific towards E2 when that's all a concerted reaction. But in terms of E1, we want our hydrogen that we will steal, to be beta to our carbocation. So since this is a conjugate base, it will have a negative charge. And for our E1 reaction, we will have our lone pairs steal that hydrogen. And since we're eliminating that hydrogen, we're getting rid of it, these electrons right here will fall back down to form our alkene between these two carbons. And from there, we now have our final product. Now, one question you also may be asking yourself is, why did we not steal this hydrogen over here? Why didn't we form an alkene between those two carbons? We could have, but the end product would be the exact same. So this is, if we were to get rid of that alkene, this would be a symmetrical molecule. So just say if we did end up forming the alkene between those two carbons, if we just flipped it over, it would be the exact same molecule. So either way, if you would have taken this hydrogen or this hydrogen, you would have ended up with the same product. Perfect. So hopefully that was a good review on some of the mechanisms in terms of how we should be approaching them. But up next, we're going to dive into providing the products for some of these reactions. So for our first one, we see that in step one, we actually have a super strong acid. We have hydrobromic acid. And then for our starting material, we also have an alcohol. Our alcohol can act as a weak base. So for our first step of the reaction, our hydrobromic acid will be our acid, and then the lone pairs on our alcohol will be acting as a base. It'll steal that proton just like that. Electrons fall back onto bromine. And as we steal that hydrogen, we create a conjugate acid. And by doing that, we now have a positive charge on our oxygen. As a good refresher, whenever you have a positive charge on an oxygen, in terms of this example, this is what's called an oxonium ion. Now, if we're looking at what we have, yes, we do have an acid, which I'm going to change those into equilibrium arrows since we're dealing with an acid-base reaction in this case. But like I mentioned, right here, we have a super strong conjugate acid. Now, what we could also look at it as is a really good water leaving group, because if we were to break this bond and we were to only have this as a molecule, it's just water. So we'll go through and showcase what that looks like when we have it leave. Electrons fall back onto oxygen, have our equilibrium arrows. And then from there, now that our water has left, we created a secondary carbocation. Now, secondary carbocations, what do we have to keep in mind? Can we undergo a carbocation rearrangement? And in this case, we can, because we do have a tertiary position right next to it on the left side. So a hydride shift will occur. And after that hydride shift occurs, we now have a tertiary carbocation, which is way more stable and super beneficial for us. And if we were to go back to the very start of this reaction, we see that right here, we had an acid-base reaction. Our electrons fell back onto bromine. So that means we still have a bromide ion kind of lingering around. Perfect. So since that bromide ion is still floating around in solution, if you will, since we have a carbocation right here, that bromide ion will go through, attack that carbocation, and we'll then get this as a product. We'll make that line look a little nicer. Maybe. Perfect. Sweet. So what we just formed is an alkyl bromide. And let's give ourselves a little more room for the next step. So keep in mind, this was all step one. And the reason I showcased the mechanism is just because it'll be very important in terms of forming carbocations, kind of doing those carbocation rearrangements. But now that we have our alkyl bromide, in terms of step two, we now have potassium terbutoxide. So that terbutoxide actually looks something like this, where we have a negative charge on that oxygen, and then that potassium is just a spectator ion floating around, not really doing much. And what we have here is we have a good leaving group in a tertiary position, and then we also have a strong base. But there is something unique about the strong base. It is bulky. Now, whenever we have a bulky base, and especially a tertiary leaving group, what can happen is an E2 reaction. But in terms of an E2 reaction, excuse me, we can either form a Zaitsev's alkene between these two carbons, or we can form the Hoffman alkene between those two carbons. So since we have a bulky base, that means we have a lot of steric hindrance. So it'll force us to form the Hoffman alkene, which will be less substituted. So we'll have our electrons steal this hydrogen, fall back on down to form our alkene. And as that's forming our alkene, it'll fall back onto bromine, kicking it out. And then in terms of our final product, we have something that looks like this. Draw everything out. And we have that Hoffman alkene, which is less substituted, since it's between these two carbons as opposed to these two carbons. Um, in terms of a good review, I didn't show any specific stereochemistry in terms of hydrogen being wedged and then our bromine being dashed, only because right here we don't have a chiral center. There's three hydrogens that we could steal. So no matter what, whatever hydrogen we steal will be antiperiplanar, especially as they're rotating around. So this will be our first product. Perfect. A good example of reviewing those bulky bases in terms of how they form as Hoffman alkenes. Now, for our next example, we have an alkene. We'll go ahead and write that on out. And we are exposing it to Br2. Now, in this case, reviewing those reactions, we won't showcase the mechanism for this one, but whenever you have an alkene and you expose it to Br2, what you'll end up forming are vicinal dihalides. So a vicinal dihalide is a super fancy way of just saying your halogens that you just added to the alkene, they are now adjacent to each other. So we have a bromide here, and then we have a bromine here. Perfect. And a good thing to note, just maybe when you're, talking about the stereochemistry of them a little later on, is that this is an anti-addition reaction, meaning they'll be facing the opposite directions. I know that this is not a chiral center, but I kind of showcased that they're on the opposite sides, just so you have that fresh in your memory. But now that we have vicinal dihalides, what we can do is look at steps 2 and 3. Now, since we have our super strong base, that NH2 group of the negative charge, it is an excess. Now, whenever we have vicinal dihalides and an excess of a super strong base, what we'll end up forming is an alkyne. So we'll go ahead, draw out our reagents. We have our sodium amide, NaNH2, an excess, and then we have a water workup step, which we'll go over in just a minute. H2O, there we go. Perfect. So what's going to happen is we'll undergo a double elimination reaction. So we already went over one elimination reaction, right? Forming an alkene. Think of it just happening again. So since we'll undergo a double elimination reaction, we will form an alkyne. And in terms of alkynes, one thing we cannot forget is that an alkyne has to be linear. So if we're looking at this structure right here, we have a hydrogen coming off of that carbon right there in a linear fashion. And then this bond is also being, it's also straight. So it's a linear geometry, if you will. And in terms of forming alkynes, I always recommend counting your carbons just because the notation can be a little tricky. So if we count our carbons in the starting material, we have 1, 2, 3, 4. And then right here, we still have 1, 2, 3, 4 carbons in our intermediate right there. In terms of having a water workup step, just say if I were to not even include that water workup step at all, if we remember back to the alkylation reaction that we reviewed after looking at that chart early on in this lesson, whenever you have an excess of a super strong base and we have this, and we have this terminal hydrogen right here, we can't forget that the hydrogen is decently acidic, especially when exposed to a very, very strong base. So if we did not include that water workup step, we would actually form an alkynyl anion, which would end up being a good carbon nucleophile. But since we did include that water workup step, we ended up forming our alkyne, which is what we wanted. And then for our fourth and final step, we have mercuric sulfate, which is our HgSO4, along with H2SO4, and then our water. Perfect. So if we remember back to those reactions, whenever you have these reagents, the goal of those reagents is to turn an alkyne into a ketone. So what we're doing is we're going to undergo a Markov-Nakov reaction because we technically have two carbons in our alkyne. We have a more substituted carbon, and then we have a less substituted carbon. And since this is a Markov-Nakov reaction, we'll add to that secondary carbon right there, the more substituted one. And for our final product, the goal of it is to form a ketone in this case, and that will be our final product. Perfect. Awesome. So for our next predicting the products question, what do we have? We see that we have a starting material and it has a wedged bromine. Perfect. And then in terms of step one, we see we have hydrosulfide, sodium hydrosulfide. Now, we can't forget that the sodium is just a spectator ion with that positive charge, and then our hydrosulfide will be a sulfur atom, or will have a sulfur with a negative charge. So we'll undergo and showcase what this will look like. And in this case, this is a good opportunity of maybe reviewing back to those SN2, E2 days when you had to decide which will happen. And in terms of this, if you remember, whenever you have a secondary substrate, it may have been annoying trying to figure out which one would occur. But the one thing we have to keep in mind is that hydrosulfide is a very weak base, but a super strong nucleophile because our sulfur has that negative charge. So since we have a strong nucleophile, weak base, SN2 is favored because E2 requires a strong base. So we'll undergo an SN2 reaction in this step. Our sulfur will attack that carbon that's bonded to the bromine, and then we'll kick out our leaving group. And then we'll showcase what this looks like. And keep in mind, in terms of SN2 reactions, one of the major things we have to be aware of is that SN2 reactions, when they undergo backside attack, it will have inversion of configuration. So if we recall back to last week's session, when we did review stereochemistry, inversion of configuration basically means you're going from the R configuration to the S configuration. You're flipping it. And in this case, we're going from a dash notation to now a wedge notation with our new group that we just added. So that's a good refresher in terms of SN2 reactions. Can't forget they require a super strong nucleophile, and then also we'll be undergoing backside attack, inverting the stereochemistry. And then in step two, what do we have? We have sodium hydride. Sodium, also a spectator ion with a positive charge. And then we have our hydride, which is a super strong base. So since we have a super strong base right here, we do have a proton right here that's bonded to our sulfur that we can go through and snag because this will be decently acidic in terms of the super strong base that we have. So our hydride will go through, steal that hydrogen, electrons fall back onto the sulfur. And by doing that, we basically just created a conjugate base. So our sulfur will have that negative charge. Perfect. We'll go through, give myself some more room. So let me kind of showcase where we're at. This was step one. This was step two. And then for step three, what we have is a methyl bromide. So we have a bromine attached to a methyl group, or CH3. And what this will be good for, kind of to keep in mind, is if we only want to add a methyl group. So what do we have right here? We have a very strong nucleophile since our sulfur has that negative charge. And then this carbon has a partial positive charge because it is bonded to that bromine. So we'll go through, undergo an SN2 reaction where our sulfur will go through, attack that methyl carbon, and then electrons will fall back onto that bromine. And in terms of our final product, this is what it will look like. Just like that, where we added our new carbon right here. Perfect. Sweet. Nice. So we only have a couple more predicting the product questions, but let's see. We also have another alkene. We'll be seeing a lot of alkene reactions just because it's good to be aware in terms of how our functional groups will be changing. But sweet, we have our alkene. And then for our first step, we have hydrobromic acid, we have a peroxide, that R2O2, and then we have heat. Now, this is a good example of why it's important of knowing your anti-Markov-Nakhov reactions, because if you know those, there's only a few to remember. You'll be able to you'll know all the Markov-Nakhov reactions. So the goal of these reagents is whenever we have an alkene, the goal is to add in a bromine. So what we'll do is we'll add a bromine, but more specifically in the anti-Markov-Nakhov position. So we'll add in our bromine right here in that anti-Markov-Nakhov position, because if we're looking at our alkene, we have a secondary position right here, and then we have our N primary position right here, and we see that we added it to that primary position. And then for our second step, what we'll show is this group. We'll draw that out actually. So we have an alkyne, which is more specifically an alkynyl anion. So how do we know it's an alkynyl anion? Because of that spectator ion. So a spectator ion, that sodium has a positive charge, which means this carbon right here, since it's a good carbon nucleophile, it'll be our alkynyl ion, which we can use to attack. So since we have a really good carbon nucleophile, and then we have a primary leaving group, this is a good example of that alkylation reaction that we did talk about early on in the lesson. And this is just a simple SN2 reaction. So our negative charge, that carbonyl will attack that carbon, kick out our leaving group, and then what we'll do is add to the carbon chain. Perfect. So we'll go through, showcase what this looks like. Carbons. And then also, good refresher of alkynes can be very tricky to draw just because we need them in that linear notation. So whenever you do draw an alkyne, like I mentioned, always count your carbons. So in total, how many carbons should we have? We should have 1, 2, 3, 4, 5, 6, 7, 8, since we added in those carbons. And if we're looking at this part of the structure, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that means we added all of the carbons correctly. And our triple bond, our alkyne, has that linear geometry, which is perfect. So we'll give ourselves some more room real quick. And then in terms of step 3, to save ourselves some room, I'll just write down 3 right here in purple, just so we know which reagents we're using. But we have hydrogen, that H2, and then we also have Lindlar's catalyst. Now, this is what we were talking about at the very beginning. Whenever we have an alkyne and we want to reduce it, we can be selective in terms of which stereoisomer we want to form in terms of an alkene. So we could either form a cis-alkene or a trans-alkene in this case. And whenever we have Lindlar's catalyst, the goal is to form a cis-alkene. So we'll copy and paste this structure. And then in terms of the carbons that we'll be having our alkene in, they'll be the ones between the carbons of the alkyne. So we're just reducing that alkyne, turning it down into an alkene. So we'll add in our groups. Boom. Perfect. And then we'll go through and count our carbons again. Remember, we should have 8 total carbons. 1, 2, 3, 4, 5, 6, 7, 8. And in terms of just practicing where your alkene should go, because I know that alkynes can be confusing, if we start on the left side of the molecule, we can use our numbering system again. So our alkene should be between carbons, well, if we were to count, we have carbon 1, and our alkene should be between carbons 2 and 3, because our alkyne is between carbons 2 and 3. And if we count, we have carbon 1, and then carbon 2 and 3 have that alkene. So that means we did it correctly. And then in terms of stereochemistry, we see that this is a cis-alkene since our groups are facing the same side. Perfect. Great example of alkylation. And then here is our final predicting the product question. Perfect. So let's start out by drawing out our cyclic structure. We see that stereochemistry will definitely play a large role in this question since we have a lot of wedges and dashes that we are seeing. So we have a wedged chlorine along with a dashed methyl group. And then we also have a dashed methyl group over here. So for our first step, we have NaOH. We have sodium hydroxide. And more specifically, we're worried about that hydroxide since our sodium spectator ion not really doing much, but that hydroxide has a negative charge and will be attacking something. So if we're looking at our starting material, our substrate, we see that it is a tertiary substrate. So since we have a tertiary substrate and a strong base, this is making me think, okay, we're going to have an E2 reaction. But more specifically, whenever an E2 reaction occurs, if we remember, we need to have an anti-periplanar hydrogen from our leaving group. So in this case, let's look at this hydrogen. Because whenever we have E2 reactions, our goal is to try and form the Zaitsev's alkene. And if we were to do that, it would be between these two carbons because those two carbons would have an alkene that's way more substituted than these two carbons. So let's look at this hydrogen right here that we'll add in. Since our methyl is dashed, that means our hydrogen has to be wedged. Now, looking at our leaving group and our hydrogen, we see that they are both wedged. And since they're both wedged, that's telling me that they are not anti-periplanar. But if we were to move over to this carbon, that's not a chiral center, and it has two hydrogens coming off of it, there will be at least one dashed hydrogen. And since we have a wedged chlorine right here and a dashed hydrogen right here, that's telling me they're anti-periplanar to each other and we can undergo an E2 reaction. Perfect. So our hydride will steal that hydrogen like that, and then electrons fall back down, forms our alkene, and then our leaving group will leave, so we'll kick out that chloride. And then by doing that, we'll copy and paste this to make it a little easier for ourselves. One thing to note is that since we did not touch this carbon whatsoever, the stereochemistry of it will stay the exact same. And then in terms of this methyl group right here, we're actually going to turn that into the straight line notation if you want to think of it that way. Only because since we formed an alkene, this carbon is now sp2 hybridized, meaning it is flat. So we lose that stereochemistry. Perfect. And then in steps 2 and 3, we'll write down, we have 2, we have O3, and then step 3, we have DMS. So these reagents are your ozonolysis reagents. So ozonolysis, if we remember, that's when you're going to cut your alkene in half, and you can now form new carbonyls. More specifically, we can form aldehydes and ketones in this case. So one way I enjoy drawing out the products of ozonolysis reactions is you can do this on your iPad, or if you have a pencil and paper. I forgot what a pencil was called after using an Apple Pencil all the time. But if you have a pencil and paper, as long as you have an eraser, you can do this. Um, but since we're literally cutting the alkene in half, we can get our eraser and split it in half. We're cutting that alkene in half. We can add in our oxygens right here, and that can showcase where our carbonyls will be going. Unfortunately, I would not recommend just leaving that as your final product. We still want to draw it out as your quote unquote straight line notation as we would normally see molecules. And the best way to do that is to just kind of use a numbering system just to make sure we're keeping track of all of our carbons. I will say how I'm about to number them. It's not necessarily anything that has to do with IUPAC nomenclature. It's just making sure I can have a mental note of where our carbons will be. So we'll just call this carbon, carbon 1, 2, 3, 4, 5, 6, 7. So what I'll do is draw out a 7 carbon chain. So 1, 2, 3, 4, 5, 6. And since I drew out 6 lines, that means we have 7 carbons. 1, 2, 3, 4, 5, 6, 7. And if we were to now add in our groups, we can actually number them first. 1, 2, 3, 4, 5, 6, 7. Perfect. So if we're looking at our numbers here and comparing them to the numbers over here, we see that on carbon 1, we should have an aldehyde. So we'll include that. And then if we move through our numbers, if we move through the structure on carbon 5, we see we have a dashed methyl group. So we will go through and include that there. And just to refresh your memory, since we did not interact with that carbon at all, we're leaving the stereochemistry the same. And then on carbon 6, we see we should have carbonyl, and more specifically, that carbonyl overall is a ketone. So that's a good way, in my opinion, to do ozonolysis questions, just to make sure you're not forgetting any of those carbons. It's just to have a numbering system and then assign those groups to whatever number you counted them on. Perfect. Alrighty. Excuse me. I'm sorry to say that we have reached our first synthesis question, but the goal of these questions is not to overwhelm you. It's just to make sure you're comfortable with being able to approach synthesis questions again, especially if you had a whole summer break or whatever it may be. So in terms of synthesis questions, the first thing I always do is count my carbons. Only because if you have a change in the number of carbons, especially if you make new carbon-carbon bonds, there's only a select few reactions that you can use to make new carbon-carbon bonds. So if we were to count the carbons in our starting material, we have 1, 2, 3, 4, 5 carbons, which we'll write down 5C just for that. And then if we're looking at this product over here, we see that we have 1, 2, 3, 4, 5, 6, 7 carbons. Did not mean to give you all the answer right there, but we have 7 carbons. Perfect. Sweet. Now from here, after I've counted my carbons, the next thing I want to do is find where is my new bond. And the easiest way to find where your new bond was added is by finding your starting material in your product. So how can we find the skeletal structure of this in our product? Well, in this case, it's kind of easy to see because we have our methyl group kind of sticking out. So we'll count. We have our 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons. So we found our starting material in our product. It's right here, which means this whole group is all new. And since that group is new, that means this carbon is the bond that we just formed. So that's our new carbon, or sorry, our new bond that we formed. And more specifically, if we recall back earlier on when we're looking at which carbons have functionality, which carbons can react, in terms of which carbon did the attacking or reacting is this carbon right here. So we'll go ahead and highlight that. And if we were to find that carbon in our starting material, we would find it right here. So in terms of the strategy and the thought process I would use is my first question is, okay, how can I include reactivity to that carbon? One thing, a little disclaimer I will note about these synthesis questions, there's probably a lot of ways that we can use to solve them. And if you guys have any other ways or have any questions, especially for those subscribed to Chemmunity, please answer or ask them in the chat. But like I mentioned, there are a couple of different ways we can use to solve this. But question is, how can we add functionality to this carbon right here? So the first thing I am noticing is that we have functionality between these two carbons right here. So let's see if I can isolate functionality on this carbon right here, that tertiary carbon more specifically. And if we're looking at the carbon compared to our alkene, this is this is a Markov-Nikov position. It is our most substituted carbon. So as a reagent we can use, we can first start off with HBr. And if we were to do that, what will happen is we're adding a bromine to that tertiary position, to that Markov-Nikov position. So we have our bromine right there. So now that we have a bromine on this carbon right here, my next question is, okay, what reaction could I use to now put functionality onto this carbon right here? We can see we're right next to it. And a good tip is that whenever you need to push functionality over by one carbon, I always recommend forming an alkene, which is something that we can do in this case. And the reason we would want to form an alkene, is only because alkenes span two carbons. And since it spans two carbons, we can now have functionality on this carbon while also having a reaction with this carbon as well. So we can use our strong bulky base from earlier, that terbutoxide. And now that we have that strong bulky base, remember that's going to form the Hoffman alkene. So that'll be our least substituted one. So we'll write that out. And after doing that, by forming our Hoffman alkene, we can see that we successfully now have reactivity or functionality on that carbon that we were interested in earlier. So if we're looking at all this, let me give us some room. My next question is, we need to add a new ethoxy group, which we can see right here. So how can we maybe turn this carbon into an electrophilic carbon? And then we can use something like ethoxide or something like that to have a strong oxygen nucleophile and maybe undergo an SN2 reaction. So if we want to form a good leaving group on this carbon, we have to be aware of where this carbon is in terms of the alkene. So this carbon, we can think of it as a primary carbon in terms of the alkene, and this one is a tertiary one. We have more substituted versus least substituted. So now we'll want to undergo an anti-Markovnikov reaction, which we can add in a bromine. So we'll use HBr, we'll have our peroxides, and then we'll have heat. And by using that reaction, we have now successfully added a leaving group onto our carbon of interest. This carbon right here was the one we were interested in, and it now has a partial positive charge. So all we need to do in terms of adding in our new group is we need to add a group that has a strong oxygen nucleophile, a strong negative charge on the oxygen. And this is kind of the beauty of synthesis questions, if you will, is that you can kind of, to a degree, make up your own stuff. So we need to just be aware that, okay, we want an oxygen with a negative charge, and we just have to keep in mind that the oxygen should have two carbons coming off of it. So we'll draw that out. Perfect. And then from here, all that's happening is a simple SN2 reaction. Take that electrophilic carbon, kick out our bromine, and then just by doing that, we now have our final product. And then in terms of the order of the reagents that we used for the synthesis question, here we go. And I even included some of those spectator ions, whether it's sodium or potassium as well. Perfect, I'm moving on. So for this one, we're going to go through, do another synthesis and providing those reagents. And we'll do what we did with that first one. We want to count our carbons. So if we're counting the carbons on our starting material, we have 1, 2, 3, 4 carbons, which we will write out, 4 carbons. And then in terms of our final product, we have 1, 2, 3, 4, 5, 6 carbons. So we have 6 carbons, we're adding our carbons, but let's see if we're adding to the carbon chain. Because next, we want to find our starting material in our product. And this one's also an easy one to find, just because we're basically looking for a triangle, if you will, in terms of that skeletal structure. And we can see our triangle right here that has 4 carbons, 1, 2, 3, 4. So since this is our final carbon, and this is the new group we're adding, this is our new bond that we formed. Now, more specifically about this bond is that it is a new carbon-carbon bond. So immediately, as I'm thinking new carbon-carbon bond, I'm thinking to myself, okay, we can use an alkynyl anion, since that's a good source of a carbon nucleophile. So to start off this reaction, now that we have our new bond, we need to find which carbon yields that reactivity, which carbon underwent the reaction from our starting material. And if we can see, since this is the new bond that we just formed, this carbon right here was that carbon that underwent the reaction, which is that carbon right there. And what's nice about this is we can see that we already have some reactivity on that carbon that we just highlighted. So now it's our goal to isolate the reactivity onto that carbon. So if we're looking at our carbon, this is a less substituted carbon. This is a more substituted carbon. So we can undergo another anti-Markovnikov reaction, which will be the exact same reagents that we used earlier, HBr, a peroxide, R2O2, and then we also have heat as well. And by doing that, we now place a bromine in the anti-Markovnikov position. Perfect. And then now that we have isolated the reactivity to this carbon only, it's our job to now make a new carbon-carbon bond. Now, this is another point during synthesis where we have to be creative. We need a good carbon nucleophile that can add two new carbons. And in this case, we can make an alkyne with just two carbons and give it a negative charge. So we'll make it an alkynyl anion, just like that. So this alkynyl anion will undergo SN2 reaction, just so we can kind of see what's happening. And now that we have that SN2 reaction, we'll form our alkyne. Perfect. And then remember, whenever you form an alkyne, I always recommend double checking the number of carbons you have, just to make sure you drew everything correctly. We should have a total of 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. And also, this right here, the alkyne is in a linear formation, it's in a linear structure, so that means we drew it correctly. So now that we have an alkyne, we see that our end product is a ketone. More specifically, that ketone is a carbonyl, and that carbonyl was added to a more substituted carbon. Since this carbon, if we were to get rid of that ketone, we could think of it as a secondary carbon versus a primary carbon. And we see right here, we can think of this carbon as a secondary carbon where it's more substituted. And then we can think of this terminal one as our primary carbon, since it only has one carbon group bonded off of it. So this is a great example of using a Markovnikov reaction that we reviewed earlier. So we can use mercuric sulfate, sulfuric acid, H2SO4, and then water. And by using those reagents, we now have our final product. That's the full list of everything we would have. And then also, when you have this strong carbon nucleophile, that alkynyl anion, when you're writing these out, just make sure you include a spectator ion, especially when you're including them above the arrows, if it's like a quiz or an exam or something like that. And then lastly, we have our final. There is a question in the chat. It says, sorry, did we add an extra carbon during the alkyne step? In terms of adding to the carbon chain or like an extra one by mistake?
Sorry, it looked like it was an extra one by mistake, but I could be wrong. Where the uh the BR left.
Ah, okay. So right here, in terms of like where this one
Yes.
is? Yeah,
Yes.
great question. So this is where it looks a little tricky in terms of our alkyne. So this carbon right here is this one where our bromine was. And if we're counting, we have 4 carbons where our alkyl bromide was. So our alkynyl anion attacked this carbon right here. And doing that, we added in these 2 bonds, and this is the new bond we formed. So in total, we should have 4 carbons. And then if we are looking at the product in terms of this step, we also have 6 carbons. 4 carbons plus 2 carbons. We have 1, 2, 3, 4, 5, 6. Does that answer your question?
Oh yeah, sorry. I was looking at it differently. I thought that the alkyne would be going directly straight up and not have that bend, if that makes sense. So I was
Yeah.
splitting
Yeah,
it.
no, no. That's a great question. And yeah, that is a common mistake in terms of drawing those alkynes. And honestly, let me actually draw that out for you. So, were you thinking something like maybe like this?
I think I just counted the carbons incorrectly there. Like the carbon where the BR is attached to, I don't think I
Yeah.
included that one on accident.
Okay. Sweet. Yeah, that makes sense. Perfect. But yeah, thank you very much. Hope that helped. And then, sweet. So for our last synthesis question, you all know the drill. We will start with counting our carbons. We have 4 carbons in our starting material, 1, 2, 3, 4. And then in our product, we have 5 carbons. 1, 2, 3, 4, 5 carbons. So 4 carbons versus 5 carbons. And this is a great example of why we should always count our carbons, because at first glance, you may be thinking to yourselves, oh, easy peasy, we can undergo a reduction reaction, but it's not that easy because we do need to add an extra carbon. So as we can see, we have our extra carbon right here, which means this is our new bond. More specifically, we formed a new carbon-carbon bond. And just like the last example, carbon-carbon bond, I'm thinking to myself alkynyl anion, that strong carbon nucleophile. And in terms of our carbons that we can, or sorry, in terms of the carbon that has reactivity, we have this carbon, as that's the one that's participating in that new bond. Then we have this carbon over here. So the question is, how can we isolate reactivity to this carbon while also making it a good carbon nucleophile? So one thing we can do, because the only good carbon nucleophile we know of so far, is to turn this alkene into an alkynyl anion, especially since we have a terminal carbon right there. So in order to turn an alkene into an alkyne first, or an alkynyl anion, what we have to do is we have to prime it for a double elimination step. So the only way we can do a double elimination step, or a good way we can do it, I should say, is by forming vicinal dihalides. So since we have an alkene, we can add in Br2. And if we remember from earlier, whenever you have Br2 in an alkene, you will form those vicinal dihalides. So we will showcase what that looks like. Br there. Then we have Br there. Perfect. And then now that we have our vicinal dihalides, we can now go through and add in those. Oops, it looks like my pen is under. There we go, having some issues. Perfect. Maybe. Sweet. Alrighty, y'all. I'm going to take a hot second to maybe reconnect my pen. It looks like it's having... Oh, there we go. We are back. Sorry about that. But sweet. So like I mentioned, we're going to set this up for a double elimination reaction. So we did something earlier to this question a little earlier on. And if we want to undergo a double elimination reaction to form an alkyne, but we don't want it to be an alkyne necessarily, we want it to be an alkynyl anion, we could include excess of our super strong base, which would leave behind a good carbon nucleophile, since that terminal alkyne, that the hydrogen, can easily be taken since it's decently acidic. So we'll add in our strong base, and we have to remind ourselves that it has to be an excess. So we'll go ahead and draw out our alkynyl anion. And then since we have our alkynyl anion right here, we'll still count our carbons just to double check everything, because those can be a little tricky to draw. Right here we have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. We're all set there. And then looking at our product, since we're adding only 1 carbon, if we remember from earlier, a really good way to add 1 carbon is just to use a methyl bromide. So we will draw out our BrCH3. Perfect. It will attack that carbon just like that. Leaving group will leave. And then by adding that extra carbon, we can now extend the carbon chain. So our alkene will actually look a little like this now. And then even though we just added 1 carbon, we'll still double check and make sure we have 5 carbons in total. We have 1, 2, 3, 4, 5. Perfect. And then in terms of going from an alkyne all the way down to an alkane, we will undergo a reduction reaction. In this case, we could have H2 with plutonium, and then we'll have that in with 2 equivalents so we can get both pi bonds. And then from there, we have our final product. So here are the reagents for that synthesis, kind of in order in terms of how you would write them down on a quiz. And yeah, that is our final synthesis question. That's it for week 2 of our weekly tutoring. And then in terms of next week, I know that a lot of y'all will be starting your classes, and this is where you get to start deciding what you want to cover. So make sure we are including your questions just so I can go over them and to help you out the best that I can. But besides that, I'll see y'all next week.
Thank you so much, guys. I'm going to put in the chat right now where you're going to find where more information about next week's live and where you can actually ask your questions. So there will be a post on tomorrow, actually, that you'll be able to start posting your questions for next week's live. It will be again at the same time, so it will be Wednesday, and it will be at the same time this one was. We'll also send out an email. We'll send out information on that community page that you'll find, and you will be notified. So again, you decide, you guys tell us what you want Cooper to cover and go over. That is the beauty of this weekly live tutoring. Can't wait for you guys to join next week, and thank you for joining. Thanks, Cooper.